All right, team, welcome. I'm really glad you could all carve out some time for this explainer today. As a senior security engineer, I've got to tell you, one of the most common and literally the most devastating vulnerabilities I see when auditing our apps is unrestricted file uploads. So today, we're going to undergo a massive mindset shift. We are totally moving away from that naive developer mindset of just, hey, let's make this feature work. And we're adopting a hardcore security mindset of assume absolutely all input is malicious. By the end of this training, you are going to understand exactly how attackers exploit upload forms and, more importantly, how we can lock them down completely.
Okay, let's dive into this roadmap. We're going to kick things off with a real-world scenario, the Big Corp upload incident. Then we'll break down the anatomy of the exploit itself, look at how to enforce strict allow lists, tackle secure random file naming, and figure out how to architecturally harden our storage locations. Finally, I'll hand over a battle-tested developer checklist for you to take back to your desks.
So first up, Section 1, the Big Corp upload incident.
Picture this. We've got an attacker. Let's call her Rachel, and she decides to poke around Big Corp's web app. It takes her literally 1 minute to find this super innocent-looking profile avatar upload endpoint. In minute 2, she realizes the system isn't really validating files securely. So what does she do? She uploads a malicious active server page, an ASP script, instead of an image file. By minute 3, because those files are just sitting in a public directory, she navigates directly to her uploaded script in her browser. The server blindly executes it. Boom! Just like that, in 3 minutes, a simple avatar upload leads to remote code execution and a total server compromise. No way we're letting that happen here.
Moving right along to Section 2, Anatomy of the Exploit.
So what's really happening here? It basically boils down to a naive mismatch in expectations. As developers, we build an avatar endpoint, and naturally we expect a user to upload a nice, friendly avatar.jpg. But attackers? They don't play by our rules at all. They're handing us a ticking time bomb. They will push executable scripts deliberately disguised as images like malicious.php.jpg. And if your code is just lazily checking the MIME-type in the HTTP request or blindly trusting the file extension, well, the attacker slips right past your defenses.
And they don't just manipulate the extension, they manipulate the entire file name using a really nasty trick called directory traversal. If you blindly trust the user's file name, an attacker can name their file .. etc. pass w or web.config. By injecting those traversal characters, they essentially trick the server into navigating backwards out of your safe little upload folder to overwrite critical system files or even drop a web shell directly into an executable path. It's a massive risk.
Now, what's really interesting about this is how effortlessly attackers bypass our first instinct as developers, the deny list. You might be sitting there thinking, okay, I'll just block .php files. Well, attackers totally anticipate this. They'll test for double extension bypasses, uploading shell.php.jpg, knowing full well that some web servers, like Apache, will actually process that inner PHP extension if they don't recognize the final one. They'll use case manipulation, tossing up a .php to bypass case-sensitive filters on Windows systems. Or they'll hit you with null byte injection, slipping a %00 right into the file name. Your validation sees the .jpg at the very end and gives it a thumbs up. But underlying systems written in C will stop reading at that exact null byte, which results in the server executing a raw PHP shell.
Let's shift gears to Section 3, Enforcing Strict Allow Lists.
Here is the absolute fundamental rule of input validation. Deny lists always fail. Always. It is practically impossible to compile a comprehensive list of every dangerous file extension across every single scripting language. I mean, you've got Perl, Python, Ruby, PHP, ASP, the list just goes on forever. Instead, you absolutely must adopt an accept known good strategy. If you're expecting a profile avatar, your allow list should strictly be PNG, JPG, and GIF. That's it. Anything else is immediately rejected at the door.
And this brilliantly illustrates how that logic actually translates into our code. Instead of trying to build this massive leaky fence to keep the bad files out, we want to build a vault. In a robust Node.js environment, for example, we define our allowed extensions array up front. We extract the extension from the user's upload. Then, we just use a simple absolute check. If the allowed extensions array does not include the uploaded file's extension, we return an error. Period. No exceptions, no overly complex regex, just a strict, impenetrable gate.
All right, on to Section 4, Secure Random File Naming.
Remember that whole discussion we just had on directory traversal?
Well, that attack is literally only possible if you take the user-supplied file name and use it directly on your server's file system. To completely neutralize this threat, you must entirely discard the user's file name. Just throw it in the trash. Generate a brand new, totally unique, random file name on the server, using a robust generator like short-id or a UUID, and then append your verified allowed extension. Now, even if the user sends crazy traversal characters or malicious payloads in their original file name, it simply doesn't matter. You've stripped them of that control.
Section 5. Hardening file storage locations. This is a big one.
I want you to ask yourselves this. Why on earth are we ever storing user files in the public web root? It's this massive legacy habit in web development to just drop uploads into a /static or /uploads folder sitting right inside the web directory. But doing this means that if a malicious script somehow magically bypasses your validation, the attacker has a direct public URL they can navigate to, triggering your server to execute their payload. It's basically handing them the keys.
So, the crucial point is we have to isolate these files. First, you need to store uploaded files completely outside the web document root. This way, they literally cannot be accessed directly via a web browser URL. Second, you've got to disable execute permissions on your upload directories. Whether you're doing that through server configurations or file system permissions, ensure that even if a script somehow sneaks in, the operating system absolutely refuses to run the thing. Finally, if users actually need to view these files, deliver them dynamically using an isolated script that fetches the file from the safe zone and serves it back with strict secure headers.
Wrapping up with Section 6, Developer Security Final Checklist.
Let's move to the county and how this builds into your new mandatory workflow. Whenever you're building or reviewing a file upload feature, this is your Bible. Step 1. Enforce strict allow lists for those extensions accepting only known good types. Step 2. Generate random file names on the server to completely defeat directory traversal. Step 3. Architecture storage so files land entirely outside the public web root. And Step 4. Disable script execution in absolutely any directory that handles user-generated content. Apply these 4 layers and you essentially eliminate the risk of a web shell compromise for good.
I really want to leave you with this final, provocative thought. Think about the specific projects and repos you were working on today. If you audited your application's file upload endpoints right now, would they survive an attacker like Rachel, or would she be running remote code on your server in under 3 minutes? Take this checklist back to your desks, review your code bases today, and let's make sure we are building applications that are truly secure by design. Thank you for your time, team. Let's get to work.